Good day, everyone. You are watching course Piezoelectric Materials, Properties and Devices. My name is Dragan Damjanovic. I would like to explain the context in which this course is given. So this is a doctoral course that I give approximately every 2 years at École polytechnique fédérale de Lausanne. The course is worth 1 credit, that means 14 hours. And the course is always scheduled to take place within 1 week, which is far from being ideal. It would be much better if course lasts the full semester, and that would allow participants to do proper homeworks and have meaningful discussions, but that is not possible for different reasons. This year I'm giving this course online, and therefore you have these recordings. Now, the piezoelectricity is a huge, vast topic, and it is not possible in 14 hours to cover everything. So I have to make a choice, and with the online course, that choice is even more difficult because there is no direct interaction with the students, and therefore I will make recordings of about 15 to 20, maybe 30 minutes for various topics, and the total length of these videos will be less than 14 hours to allow students to follow, to think about the course, and during the course, the EPFL students can have access to me during regularly scheduled hours and ask questions. My goal here is, since students have such vast difference in backgrounds and interests, is to give enough background for people interested in applications, in fundamental stuff, in materials, that they can navigate the world of piezoelectrics by themselves after this course. I will certainly miss many topics that are of interest to some people, and may probably spend some time on the topics that are of less important for other people, but these are the choices we have to make. I'm certainly going to make some errors while I'm speaking, and there are certainly errors in slides, in view graphs that I'm presenting to you. So I would appreciate it very much if you spot any errors to let me know. Here is my email address. You can also use it to send comments, and also, which is very important, to ask questions, and I will try to answer. I'm giving you some references here. This is not an exhaustive list, but gives references that I think are important for the field. The first group of the references concerns a general topic of piezoelectricity, or other topics that are related, like ferroelectrics. You have 2 books which discuss symmetries, the formalism that is important for piezoelectric materials. The second book by Nunem also talks about materials, while the first book by Nye less so. One book is on ceramics. There is a lot of processing there, and the other books go into from fundamentals to devices. The second category are books by Chino, where you can find a lot of phenomenological approaches to describing piezoelectric materials and devices, and description of a lot of devices that may be of interest, such as actuators, motors, optical devices, and so on, but all of them one or another way related to piezoelectrics. The third group of references is actually written by people active in industry. So if you are interested in applications, these are the references that can be very useful to you. And the final two references are written by myself, and they cover some topics on hysteresis, piezoelectric hysteresis, that you cannot probably easily find at other places. There is another reference review paper in the Journal of American Ceramic Society in 2005 on the contributions to piezoelectric effect, which I haven't listed here, but which may be of interest to you if you are interested in a more fundamental aspects. So that would be Journal of American Ceramic Society, 2005. I am giving you some symbols that I will be using throughout the course. You will notice that some of these symbols, that some functions like strain have several symbols. I do hope that this will not create any confusion, and that from the context you will able to follow. Some symbols are common for two different functions, for example, epsilon for dielectric permittivity, and also for strain. But again, I think from the context you will recognize where you are. I would like to focus on some scientific and engineering aspects of piezoelectric materials in my course and build course around that. One of them is that majority of the piezoelectric materials are complex, really chemically complex, and very rich with the properties. Others are more simple, but still you will find that overall piezoelectric phenomena are rather complex. The origin of piezoelectric effect in these materials is not always well understood, very often on all levels. Chemistry and atomic or molecular, in structure, even symmetry is not known very often in some materials. These materials contain interfaces such as domain walls, and these interfaces can move under external fields, electric and mechanical fields, and they contribute strongly to the piezoelectric effect, producing hysteresis, frequency dispersion, nonlinearity, which are usually undesired in devices, and we have to learn how to control them, avoid them, or compensate for them. Some aspects on piezoelectricity are now important that touch environmental issues and biocompatibility, and this is in part, for example, replacement of lead with non-toxic compounds. As it turns out, some of those non-toxic compounds can be environmentally friendly, and again, we have a pretty complex situation there where it is very difficult to find true replacement for lead-based materials. Since piezoelectric effect is encountered in polymers, biological tissues, and in solid materials, obviously the origins must be different, and there are a multitude of mechanisms that can contribute to piezoelectricity. in organic materials, in biological materials, it is not clear if piezoelectricity plays any physiological role in the living organisms. An interesting thing is that even though we are focusing here on one phenomenon, piezoelectricity and related processes, many problems of actuation, sensing, and energy conversion transducers are common regardless of underlying physical principles. And so this course will hopefully be useful for you one way or another, even if you are not ever going to work with piezoelectric materials. And finally, I know of very few properties that have such a vast number of different applications, different devices that can be built based on this effect, and the piezoelectricity is really remarkable material in that aspects, and we will spend a lot of time discussing different effects. I will just very quickly go through a few examples to show you some diversity. For example, you can use piezoelectric materials, tubes for scanners that have a very precise sub-nanometer angstrom precision of moving parts. In this particular case, you have a tube with 4 electrodes which are separated, and then by applying electric field on the different combination of these electrodes and a central electrode which is inside the tube, you can bend this tube in different directions and get a scanner which has very high precision. Another example are piezoelectric multi-layer actuators that are used in fuel injection actuators. Here is a picture from Bosch. We will spend some time on actuators and multi-layer actuators because they have some specific properties, failure mechanisms, exactly because of this multi-layer nature. And it is interesting to see how these things are handled and problems solved. Also, they are associated with hysteresis and the creep. And we will see how we can modify our materials to make these issues less severe. You can combine piezoelectrics with other materials, for example, with the polymers to make very light, very soft structures. And these are easily deformable structures that can be very sensitive as a sensors or give large charges for energy harvesting and subsequent storage. Another group of applications are at high frequencies up to megahertz range, where, for example, underwater, so here we are talking about maybe kilohertz range, tens of kilohertz range, where big objects are probed and looked for. Here is a picture of a ship on an ocean floor. In a sonar, and exactly same type of device, very often with a similar architecture, is used in a medical imaging, where we are working with tens or even hundreds of megahertz, for example, in ophthalmology, to observe fine details of a human eye. They are also used in addition to ophthalmology in the dermatology and so on, where you really want to see very fine features. And these can be now used for observation and for diagnosis. So great progress has been made recently, and we will discuss what kind of materials, piezoelectric materials, can be used here. Another application is in timekeeping. Here is a quartz resonator that is used in watches. Here you have a acoustical fork which oscillates, which has a piezoelectric resonance and oscillates with a certain number of times per unit time per second. And by counting these oscillations, we can measure time very precisely, much more precisely than with any mechanical system. Finally, here is a cool example of a cooling jet by General Electric, where you have two piezoelectric elements which are joined together with a small space in between them. So here you see the upper one, and there is another one below. Here is a piezoelectric material which is glued on a piece of metal, and then by applying electrical field and bending this, you can make air being expelled or brought inside, this creates airflow which can cool your computer. So instead of using a ventilator, which makes a lot of noise, you can use these almost silent devices. I have mentioned several times so far how complex piezoelectric materials are, and I want to make an illustration of this here. Here is a piezoelectric ceramic which is widely used for many applications. And in order to predict properties of this ceramic or explain properties of these ceramics, you really have to go from the bottom, from atomic scale, understand the atomic scale structure, how crystal is arranged, identify any domain walls. These are interfaces that separate strain and polarization, homogeneous regions in a crystal with a homogeneous polarization and strain. Here you see many of these domain walls, which when you apply electric field or pressure will start moving, because they are both electrically and mechanically active. They'll start moving and contribute to the piezoelectric effect. And this we will study in details. And then when you put all these grains together and you make ceramic, you find out that all these grains are oriented in different directions, and therefore they will all deform under external field by a different amount. And therefore you have some dynamics inside this ceramic, where every grain is pushing every grain. So it's actually quite difficult to keep track of everything that is going on there. What you should remember is that to explain piezoelectric materials, piezoelectric effect, you have to go across the scales, atom, domain wall scale, grains, sample size, sample scale, which is in millimeter, grains in micrometers, domain walls in nanometers, atoms in sub-nanometers or picometer side, and you have to cover all these scales. Of course, the progress that has been made in science, both in theory and experiments, is huge, and now we know much more than we did before. We can calculate exactly what is environment of every atom. And you see here, for example, you have isostructural barium titanate and lead titanate, both tetragonal perovskites at room temperature, but barium oxygen and the lead oxygen environment are different, and this actually creates huge difference in properties between these lead-based and lead-free materials. It is encouraging that now we have tools with which we can understand this much better. But also experimentally, with scanning transmission electron microscopy, we can now see individual atoms, and in those individual atoms, we can measure their displacements from ideal positions. And here we are measuring titanium. These are small spots that you actually cannot see because there are arrows in all of them, and that means that all of them have been displaced from their ideal cubic positions in this particular material, and you see it better here. So these displacements correlate, and they make polar nanoclusters in a material which respond to electric field, giving a piezoelectric response, dielectric response, and mechanical response, in addition to that of what would be obtained by having atoms in an ideal crystal cell. Phenomenological studies of thermodynamics or other are also very useful in studies of piezoelectric materials. Especially the topic morphotropic phase boundary has been widely studied with phenomenological models, and really a lot of understanding that we have today we owe to these phenomenological models. We will spend a lot of time discussing morphotropic phase boundary concept, the phase diagram, why we have that piezoelectric properties peak at this morphotropic phase boundary, and we will be able to explain that at least up to some level. And finally, I want to finish this part by asking you to read this paper, More is Different in Science by Philip Anderson, who basically makes a point that when you start putting objects together, if there are some interactions between them and so on, very soon you will get new emergent phenomena that you cannot that easily predict just by summing up the parts, functioning of those parts. And that works not only in material science, but across the fields. So you can differentiate between reductionism and emergent phenomena. You can always reduce solid state physics to elementary particle physics, to protons and electrons and quarks. But to put together quarks and electrons and to get piezoelectric ceramic is much more difficult. And that works everywhere, all the way to let's say molecular biology, cell biology. We can separate the brain into all molecules that it consists of, but if you take molecules, you cannot easily put them together and get brain and consciousness and so on. So I think this is a very interesting paper to read. It's only 2 to 3 pages long, 3-4 pages long, and if you just type this in your browser, you will get a PDF file of this paper. So I end up this session actually with this outline of the course. We will go with some basic definitions. I will give you some thermodynamic relations. We will define piezoelectric effect through thermodynamic relations. They are very useful because they will allow us to study symmetry of piezoelectric materials, crystalline isotropy. We will see how we can get piezoelectricity in non-piezoelectric materials, how we can go with the higher order electromechanical effects. We will discuss a lot coupling of piezoelectricity with thermal, mechanical, other electrical variables. And we will study piezoelectric response under different boundary conditions. This is extremely important for applications, and you really cannot understand how your device is working if you don't understand these boundary conditions and coupling with of piezoelectric material with its environment. Then we will discuss piezoelectric materials, ceramics, crystals, films. We will mention a little bit polymers and composites. We will talk about ferroelectric piezoelectrics. That's the widest family of piezoelectric materials. In relation to that, we will discuss some structure property relations, morphotropic phase boundary, and ferroelectric domain walls. And that leads us to these different contributions to the piezoelectric effect, which are manifested with piezoelectric hysteresis, nonlinearity, and frequency dispersion. And then finally, but not necessarily in this order, we will talk about, give examples of many applications. We will talk about applications in almost all these parts. So everything is really intermixed. So this is the fine of this first video, and the next time we will go with the thermodynamic definition of the piezoelectric effect.